Hello everyone, my name is Deng, and today I would like to talk about budgeted learning for developing personalized treatment. First, I will give a big picture of the field of personalized medicine, and then I will present a case for using budgeted learning techniques in machine learning for designing more efficient clinical trials in this field. And after that, I will formulate a simplified problem, and I will present some experimental results. Let me first describe what is a budgeted learning problem in machine learning. The term of budget learning was proposed by Russ Greiner and his colleagues to describe the following scenario. A learner is given a fixed amount of assets to explore. Afterwards, the learner has to stick to the model that he has built and deemed to be best. Here I have listed 3 examples. For example, a learner may be given a certain amount of money to run a medical test in order to build a predictive diagnostic model for some disease, after which he has to use this model to diagnose new patients. Let's first go over a big picture of the field of personalized medicine. One of the greatest challenges in treating chronic diseases such as diabetes, depression, is that one size does not fit all. What this means is that drugs, treatments work drastically differently on different types of patients. Researchers and clinical scientists are compelled to look for factors that can differentiate these patients. And these factors include medical history, lab work, neuroimaging, psychosocial factors, etc., etc. Computer scientists also work with clinical scientists to run different types of marker discovery algorithms to divide a general patient population into categories or profiles. And the goal here is to give the right treatment to the right type of patients. So once we have profiles of patients, or different categories of patients, why do we need further trials to evaluate the usefulness of these patient profiles or categories? There are several reasons. Treatment differences discovered through data mining are often spurious due to small sample sizes, multiple testing, and some other causal confounding issues. Secondly, it is also expensive to run one trial for each individual profile of patients, or one trial for each individual drug. As a side note, sometimes running one trial for a particular profile of patients, or running one trial for a particular drug, is what is being done in the field. However, this is quite inefficient. So here are some of the characteristics of a trial for evaluating the usefulness of putative profiles. The objective here is to evaluate the usefulness of patient profiles for treatment selection. The performance measure here is something that can tell us what may be the best treatment for each patient profile. From a machine learning perspective, the experience used in learning is patient treatment outcomes over a clinical trial period. And here we propose to use a budgeted design. So here is a description of a simplified budgeted trial design problem for developing personalized treatments. There are 2 treatments, A and B, and there are K distinct patient profiles, 1 to K. For each I, for each patient profile I, and for each treatment S, which takes value of A or B, the clinical outcome of treating patient from profile I with treatment S is a random variable denoted by YIS. Y_IS is a random variable. In this paper, we assume that it is distributed as a normal random variable with mean mu is and variance sigma epsilon squared. So the letter mu is a mean vector of treatment effects for different profiles and different drugs. For example, mu1a is the mean outcome or the expected outcome for patient profile 1 using treatment A, etc. Okay, let's define what is a budget learning trial design, B. The core of it is that we have a budget, i.e. a sample size 2t. In other words, we are only allowed to recruit up to 2t number of patients. And the budget learning trial design B is a tuple E and D, with E being the exploration rule and D being the final decision rule. So here are some notations. XT is used to denote a history of patient outcomes and recruitment after time t. E_t, X T is a decision rule per time t, which suggests from what biomarker profile, from what profile to recruit the next 2 patients. And finally, D, which is a vector of K components, is the final decision rule that says what treatment is to be used in the future for each of the profiles. So here is a animation. So time goes from 0 to t-1 time steps. Patients are recruited from each profile, and E_t, capital XT, tells you from which profile to recruit the next couple of patients. And at time t equals to big T, the decision rule D says for each of the K profiles, what is to be the treatment used for treating future patients. We finished the definition of a budget learning trial design by defining the loss function L with respect to the final decision rule D. Here, L, mu of D says the loss of a design is the sum of the losses over K profiles, where for each profile the loss is defined as a difference between the selected treatment and the treatment that is not selected. In other words, if we have selected a treatment that has a higher mean outcome than the other treatment, then the loss is 0. Otherwise, the loss is the difference. And finally, as a Bayesian design, the risk is just the expected loss. Here, the expectation is taken with respect to the prior and the decision rule B. Notice that in Bayesian methods, the expected mean treatment is itself a random variable with a prior rho. And in practice, we can choose rho to be an non-informative prior. And the goal here for optimizing a budgeted learning trial design is to find B, find this exploration rule and decision rule combo that minimizes the Bayes risk R. So let's first talk about the final decision rule D. It turns out under fairly general assumptions about the prior rho, the optimal final decision rule is quite simple. Given the patient history, XT, the optimal decision rule for a profile I is simply by selecting the treatment that has the higher posterior mean outcome. Notice here the capital T is to emphasize that mu is a posterior mean. To calculate the exploration rule E is a much harder problem. And even for Gaussian prior, there is no closed form solution, and exact computation can be quite difficult. So here's an intuition for one particular algorithm called look ahead, described in the paper. What this algorithm does is that at time t, anticipate the possible outcomes of the next n pairs of patients and calculate the Bayes risk for recruiting the next n pairs of patients. The Bayes risk here depends on the allocation configuration for these m pairs of patients. For example, suppose m is equal to 3 and k is equal to 2. There are 4 possible configurations: allocating 0 to the first profile and 3 pairs to the second profile, or allocating 1 to the first profile and 2 to the second profile, etc. There is a formula for this particular risk. The risk of recruiting the next n pair patients can be written in such a way, and in this formula, sigma I ni is the new posterior variance of allocating ni out of m pairs of patients to profile I, and delta I is the difference of posterior treatment, and small phi and big phi are the PDF and CDF of standard normal. Delta I is the negative of some difference in mean, and this term is smaller if the difference is bigger. Okay, so what that means is that if the treatment difference is big, then the risk is small for a particular profile. Okay, also notice sigma I is the posterior variance of profile I, and if a profile has not been explored enough, then sigma I will be big. So look ahead algorithm will pick the next profile that reduces the risk the most. Next, I'm going to present some experimental results based on a real clinical trial called nafazondone CBASP trial. This particular trial studies treatment options for depressed individuals, and the sample size in the original clinical trial is 440. Here's a summarization of a simulated population based on this particular trial. And the patient characteristics used to form patient profiles are obsessive compulsiveness, OC, alcohol use, which takes discrete values of absent, abuse, and dependence. Based on these 2 characteristics, patient population are divided into 4 subpopulations: profile 1, profile 2, profile 3, and profile 4. Okay? And there are 2 treatments. One of them is called NFZ, and the other one is called combo. Okay, and notice, one thing to note is that combo does not mean that it will work better than NFZ, okay? And by looking at the mean outcome of the actual clinical trial, we noticed that the difference for profile 1 between using NFZ and combo is quite small, and the difference is slightly larger for the other 3 profiles. So we make the assumption that there is actually no difference in profile 1. In other words, both treatments are equally effective. So here is the end result of one of the simulations that we run. On the x-axis, we have the sample size, which is how many patients have been recruited into the trial so far. On the y-axis, we have the decision risk as defined in the previous slides. The algorithms compared here are the LA algorithm that we described, and UR and UR balanced, which are uniformly random selecting any profile and a variant of this algorithm. As we can see here that the algorithm LA is able to reduce the risk far more efficient than the other 2 algorithms, and using 200 patients, it is already enough to significantly decrease the decision risk such that you could tell apart, very easily tell apart, what treatment should be used for what profile. And that's it. Thanks.